Okay, so section 8.4 on page 436. And this one is called Finding the Sums of Infinite Geometric Series. And you might think, well, that's kind of a dumb activity. If it's infinite, it's not going to add up to anything. This is a pretty cool little lecture, and it's kind of interesting to understand what's happening. And I think I'm going to lead off with what people anciently and still people today, if they're not thinking really carefully, can still sucker for. It's called Zeno's paradox. And Zeno was he was a smart man, but he was always trying to mess up the great philosophers. Like, he would wander around and he'd mess up Socrates and his buddies that were following him, and not mess them up, but try to, with things called a paradox. Do you know what a paradox is? You do or you don't? Let me give you one. I'm sure that if you are a believer in a higher power, that he looks down on us and says, you think you're so clever, or he just shakes his head, kind of like I would my little outlet if she made a joke. But if you are a believer in God, do you believe God can do anything? We've been told that's called omnipotence, right? But here's a question for you. Can God build a rock so big that he can't lift it? If he can't build a rock, then there's something he can't do. If he can build a rock and can't lift it, there's something he can't do. So that's a paradox. It's weird. It's strange. And that's not the only type. But Zeno, this thinker, was always trying to foil and mess up the great philosophers. He offered lots and lots of different paradoxes that took people a lot of thought. And sometimes they never did figure it out. They just left scratching their heads. So here's one. This is his most famous one. Zeno of Iliad, circa 550 BC, 450 BC, so that's a long time. Before Christ, long time. 450 BC, is credited with creating several famous paradoxes, but by far known is the paradox of the tortoise, is the great Greek hero of Homer's The Iliad. Anybody experienced the Iliad yet? You know who Achilles is? Very fleet of foot. And if you watch the movie Troy, it's rated R. If you watch the movie Troy, played by, what's his name? Gosh, I can't remember what his name is. I got up to it and I'm really tired. It's a really good looking, but he's more my generation.
Brad Pitt?
Brad Pitt, that's the one. Brad Pitt played Achilles. Yeah, Brad Pitt played Achilles and did a really good job with it. Very fleet of foot. He was a lot smarter in the movie than it's portrayed here. But Achilles was he's a great warrior. Anyway, here comes. It has inspired many writers and thinkers through the ages, notably Lewis Carroll. You know who that is? He wrote Through the Looking Glass. And Douglas Hofstadter, I've heard that name, but I don't know what he wrote, so don't ask me. They also wrote dialogues involving the tortoise and Achilles. The original story goes something like this. So here's the story. Try to do the math that's in it and see what happens to you. The tortoise challenged Achilles to a race, claiming that he would win as long as Achilles gave him a small head start. Achilles laughed at this, for of course he was a mighty warrior and swift of foot, whereas the tortoise was heavy and slow. How big a head start do you need? He asked the tortoise with a smile. 10 meters, the latter replied. Achilles laughed louder than ever. You'll surely lose, my friend, in that case, he told the tortoise. But let us race if you wish it. Oh, on the contrary, said the tortoise. I will win, and I can prove it to you by a simple argument. Go on, then, Achilles replied with less confidence than he felt before. He knew he was a superior athlete, but he also knew that Tortoise had a sharper wit, and he had lost many a bewildering argument with him before. Suppose, began the tortoise, that you give me a 10-meter head start. Would you say that you could cover that 10 meters between us very quickly? Oh, very quickly, Achilles affirmed. And in that time, how far should I have gone, do you think? Perhaps a meter, no more, Achilles said after a moment's thought. Okay, replied the tortoise. So now there is a meter between us. and you would catch up that distance very quickly? Oh, very quickly indeed. And yet, in that time, I shall have gone a little way further. So that now you must catch that distance up, right? Yeah, said Achilles slowly. And while you are doing so, I shall have gone a little way further. And so you must catch up that new distance, the tortoise continued smoothly. Achilles said nothing. And so you see, in each moment, you must be catching up the distance between us, and yet I, at the same time, will be adding a new distance, however small, for you to catch up again. Indeed, it must be so, said Achilles wearily. And so you can never catch up, the tortoise concluded sympathetically. You are right as always, said Achilles, to the race. What do you think of the argument?
I think you could have won the race. I don't know how far it was.
Maybe. But think about a turtle, and think about Achilles, and 10 meters, that's less than the width of this road.
I've heard that before, and I just thought all they're doing is slowing down time.
Yeah, you could argue it that way, and we're not gonna be doing that. Slowing down time, we're gonna be looking at the map, and it's much simpler than that, but when I heard it first time too, I was thinking, how does that work? Let me tell you that they've got another one that may bring home the paradoxicalness of this to you. We'll talk about time if you want to later. Zeno's paradox may be rephrased as follows. Suppose I wish to cross the room. So let's say I want to cross the room to get out the door. So that's my goal. Okay. First, of course, I must cover half the distance. That's about right here. Then I must cover half the remaining distance. That's about right here. Then I must cover half the remaining distance. That's about here. And then half again. And then half again. So each time I got to get at least halfway, and I keep getting, and I cut this in half, and I cut this in half, and I cut this in half, and I keep cutting it in half forever and ever and ever, and I can never get out the door. So you guys are trapped in here forever. You've always been able to get out before. So what they're saying is, if you take something and you keep cutting it in half, and you keep doing it forever and ever and ever and ever, you keep adding a little bit more distance each time. And the distance is smaller, but you keep adding something. And so the idea is, it just keeps getting, because you keep adding something, no matter how small, that the result just gets bigger and bigger and bigger and bigger and bigger, because you go into infinity. And that's the fallacy. Look at this, graphically speaking. I'm going to draw a really exaggerated number line. This might be your thoughts of slowing down time. I'm going to start here with 0, and I'm going to draw this number line out here, and I'm not going to put a 1 till right here. It goes a little bit beyond. So here's the number 1. This is my monstrous number line. Okay? We're going to just deal with a distance of 1. And so what I'm going to do is I'm going to figure out what happens when I take 1/2. I'm going to do it geometrically and numerically here. So 1/2, I don't know, does that look about right? Maybe? Okay. So this is the 1/2. To that, I'm going to add half of that, which is about right here, and that's 1/4 of the 1. Then I'm going to add, so this is 1/4. Then I'm going to add half of that, and that would be 1/8. Are you with me? Yeah. So I'm going to add 1/8, and then I'm going to add 1/16, and then I'm going to add 1/32, and then 1/64, and then 1/28, and then 1/256, and then and so forth, like that, forever and ever. And I'm going to keep adding something to that. And it makes people believe that the sum continues to get larger and larger and larger, and it does not. What does it arrive at when I've added up all these things I keep cutting in half? Where do you arrive? At 1. These things which go on for infinity, forever and ever and ever and ever, add up to, I guess I should do this, add up to 1. They don't add up to infinity. You have to get to infinity before it arrives at 1. You're always somewhat less than 1. But it is not an unknown number, and it is not infinity. And so the argument that no matter how much you keep adding on extra pieces, it keeps getting bigger and bigger and bigger, it doesn't. What it is it's approaching something.
So would it always be one or whatever like the next number is you're going to?
Yeah, but you can't get past it. You can only get closer to one by keeping adding these fractions. You can only get closer and closer and closer and closer to one. So if you let this go on to infinity, which is what this indicates here, the result is one, not infinity. Even though you keep adding something to it, you're not adding extra numbers, you're just approaching a limit, we call it. So that's the paradox solved, and of course Achilles would win, and of course we can get out the door. Because we're not approaching infinity, we're approaching a definite value, which is probably about 13 meters. From there to there. That's what we're approaching, it's not an infinite thing. If that still didn't make much sense to you and you're still wondering about it, don't worry. You can still do the assignment, and you can still do these problems on the test and do just fine. Here is what we're going to take a look at here. I need you to do a little bit more infinite type thinking with me for just a minute. Because, do you understand, I didn't make a point of this. Do you understand that this sequence that I have here, and there are many, many others, but do you understand that this sequence or series that I have right here is geometric? And that A1 is 1/2, and so is R. Okay, you with me there? And N is infinity. So I'm going to erase this because what I'm about to tell you is only true for geometrics. But we see a lot of those going to infinity. Here's the deal. If I take the formula for the nth term, sorry, not the nth term, sorry, the sum of n terms for the geometric. Sum of n terms is equal to A1 times 1 minus r to the n over 1 minus r. Would you agree with that? Okay. Now, I want you to imagine that I change this, not to n, that would be a describable number. But if I change this to infinity, now you're going to have to use your imagination a little bit. That means this changes to infinity. And if r is a proper fraction, got an idea in your mind what a proper fraction is? 2/3 is proper, 5/3 is not. You with me there? Means it's less, the value of it is less than 1. So if the r value is a proper fraction, like 1/2, like I did before here, if I do 1 minus 1/2 raised to the infinity, or a very, very large number, or however you want to think about it, if this thing that I keep powering over and over and over again is less than 1, then every time I use it, every time I multiply by 1/2, whatever I had before gets smaller. Doesn't it?
Yeah.
If I do that an infinite number of times, won't this thing right here go to infinity? Go to 0? See, look, just this piece right here is all I want to focus on. Just that chunk right there. What does that mean? If you think of this as a large number rather than a strange, bizarre idea of infinity, just a really big number, let's say, not really big, let's say 8. I know 8's not really big. But if you take 1/2 times 1/2 times 1/2 times 1/2 times 1/2, 1, 2, 3, 4, 5, is that only 5 feet? Half times 1/2 times, that's a 2, times 1/2. What you'll end up with is 1, little tiny old 1, over 2 to the 8th. That's a pretty good sized number. And 1 over that really big number is getting closer and closer and closer to 0. Would you buy that? Would you buy the fact that 1 over 2 to the 8th is bigger than 1 over 2 to the 20th?
Yes.
And that's bigger than 1 over 2 to the 10,000.
Yeah.
And that's bigger than 1 over 2 to the infinity. And 1 over 2 to the infinity is 1 over something so large that this is virtually 0. Have I convinced you? So 1 over 2 to the infinity goes to 0. What's 1 minus 0? 1. So we end up with A1 times 1 over 1 minus R, which is A1 over 1 minus R. If I multiply this times that fraction. Do you agree with that? So using the old formula and letting n be extremely large and, well, then this is what I get. I'm going to erase this stuff over here. This is what I get for simplifying that and letting the fraction or the power go to infinity. I end up with the sum of infinite terms geometrically. This is still geometric. The sum of infinite terms is going to be A1 over 1 minus R. If, and I mean big if, R is a positive or negative proper fraction. R is beyond this range of values, and this doesn't hold. It goes to infinity. It has no sum. Because if R is bigger than 1, and you multiply by an infinite number of times, you are getting bigger and bigger and bigger and bigger and bigger. So yeah, it adds to infinity. The whole idea, the whole premise behind all of this was that R had to be a proper fraction of some kind, so that every time you use it, you keep getting something smaller and smaller and smaller, headed to 0. Otherwise, this argument makes no sense. So this is this formula for the sum of an infinite geometric series if R is between -1 and 1. Now in the book, they'll describe it like this. If the absolute value of R is less than 1. It says the same thing. If R is a proper fraction, positive or negative, then its absolute value is less than 1. It's the same expression. I don't care which one you look at. They're both the same thing. But it is a huge if, because you can stumble. If you decide to use this formula on something where R is greater than 1, you'll still have something to calculate, and it'll be wrong, because there is no sum if R is greater than 1. Because the numbers just keep getting bigger. So keep adding on bigger and bigger and bigger number, you go to infinity. All right, so let's practice with a couple of these. I'm going to leave that up there. A couple of examples. So here's one, and so they're offered in several different ways. Here's one in summation notation. So you got to remember how to read this, geometrically speaking. I equals 1 to infinity. Oh, we're going to infinity. Of 3 times 0.7 to the I minus 1. Okay, so since we're going to infinity, that means the only formula that we can consider is this one. This is the only one that allows us to go to infinity. So the question we got to ask, first of all, does R fit the bill?
Yeah.
You say, well, I don't know. What is R? What is R? It's the 0.7. So it fits the bill, right?
Yep.
Did somebody say something to me? What?
Sorry.
Okay, all right. So if y'all can recognize the R in here and it fits the bill, it's between -1 and 1, which it is, then we can use this formula. But we need two things. We need A1 and R. A1's easy to come by in this as well. What's A1? If you put 1 in for I, you get 0.7 to the 0, which is 1 times 3 is 3. So this is equal to 3 over 1 minus 0.7. Which is 3 over 0.3. And that is 10, isn't it? Is it? Okay. So if you start out with 3 and multiply by 0.7 and multiply that by 0.7, I don't know what that is. Anyway, and put it here and put it here and keep going forever and ever and ever and ever and ever, they will be approaching the number 10 as you add these up over and over. That's what's saying. Okay? So that one had the big if satisfied, so we were able to use the formula. Let's try another one. This one's not offered to you in summation notation. It's offered a different way. 1 plus 3 plus 9 plus 27 plus forever. What's that going to add up to? Infinity. Or in other words, this has no sum. That's how they're going to want you to put it. Big Ideas Math, and that's how we answer it on the test. Has no sum. How come it doesn't have a sum? Because R is bigger than 1. That's why. That's the answer to the question. It doesn't have a sum because R doesn't fit the bill. R is what? What's R in this?
2. Oh, no.
3 is the multiplier, isn't it? Every time you multiply the successive number by 3, that's R. Now, let me show you, though, that you could use that formula and you get the wrong answer. And if you do that on the test, you'll miss the whole problem for not recognizing that R didn't fit the bill. If you decide, okay, that's an infinite, I see the dots, I'm going to use the infinite one. That would be the first term over 1 minus the common difference, or the common ratio, which is 3. So that's negative what? Negative 1/2. Put that in the blank, you'll miss it all, because this has no sum. You plug it in the formula and get something totally wrong. Okay, so that one doesn't have 1. Let's try this one. 1 minus 3/4 plus 9/16 minus 27/64 plus forever. Let's follow that pattern. Does this have a sum? Well, we got to figure some things out. We can see A1. It's fairly clear. I'm not worried about that. It's the R that I want to figure out. So I gotta find it. How do we find R?
You do like
You take,
divide 1 by the other.
negative 3/4 times.
Yeah, you could take divided by 1, and that would give it to you. Yeah, that would give it to you as well. Negative 3/4 divided by 1 is negative 3/4. And notice that negative 3/4 times negative 3/4 is positive 9/16. And positive 9/16 times negative 3/4 is negative 27 on the top and 64 on the bottom. That's why the signs are alternating, because your R is negative.
Yeah.
Does that fit what we need to apply the formula? It does. So our formula, this thing is going to add up to, well, I'll go ahead and write it here. It's going to add up to 1, because that's the first term, over 1 minus 3/4, which is really plus 3/4. 1 minus a negative, right? And 1 plus 3/4 is equal to, as an improper fraction, this is 4/4 plus 3/4 is 7/4. So this thing will add up to 4/7 when you invert multiply. Now this one's a little bit odd. If you were to put this one on a number line, just for your information, if you were to put that one on a number line, you would start out at 1, and then you'd go back 3/4, and then forward 9/16, and then backward 27, back over to here to 27/64, and then forward to the next one, and then backward and forward and backward and forward, and you would land. Well, the numbers all the way through would add up to 4/7. That's where you'd land, is at 4/7. Okay. Okay, let's try 2 more examples. This is a real life type problem. It's kind of cool, kind of fun. This has to do with a swinging pendulum. It also has to do with, for example, bouncing one of those really lively rubber balls that you can get, the little ones you get out of the machine that you used to love when you were a little kid.
Yes.
Maybe you still love them, I don't know. And when you bounce them, they never quite return to the height that they were the previous bounce, right? That's due to the conservation of energy. Every time it hits, it loses a little bit of energy because of friction, sound, compression, all kinds of stuff. And it's impossible for it to return any higher than the previous bounce. It's always somewhat less. That's similar with a pendulum. If you've got something on the end of a string and you hold it out, that thing's going to swing and it'll eventually slow down. You've had that experience by sitting in the swing yourself, right? You'll eventually stop. Okay, so here's the scenario. A pendulum that is released to swing freely travels 18 inches on the first swing. On each successive swing, the pendulum travels 80% of the distance of the previous swing. What's the total distance traveled by the pendulum? You're going, well, it keeps getting smaller and smaller and smaller, but it just keeps swinging. It'll travel an infinite. No, yeah, you're falling into the paradox again. So here's our situation. Starts out at an 18-inch swing. That's a 1, folks. It returns 80%. It'll swing. If it starts out and swings 18, then the next swing back it will be 80% of 18. And whatever that number is, the next swing back will be 80% of that. So that it slows. What they're telling you with that 80% is R. And R fits the bill for our equation, and we assume this pendulum will keep swinging virtually forever. The biggest possible distance it can travel then is 18 over 1 minus 0.8, which is 18 divided by 0.2, which is 90. Isn't it? Is that true?
Yeah.
So even if we let this thing keep swinging forever, never, it will never, the total swing distance will never be more than 90. If you added up all the swing lengths. It's kind of cool. Okay. Example 4, and this last one, I really, I'll show you. No, I don't want to show you. I just want to tell you. Because it's not worth it. People don't remember the proof of it anyway. It has to do with geometric sequences, I'll tell you that. But I want to show you something kind of cool. Check this out on your calculator. This last part, this last little tiny chunk is on your test. And I want you to remember it forever. But what I'm about to show you has nothing to do with geometric sequences, at least the way I'm going to teach it. Okay, it does have something to do with it, but nobody ever remembers it. So this part is separate from everything else I've done. So it's a totally different idea. Can anybody tell me what 0.3 repeated is as a fraction? You guys know that one. Okay. What is 0.6 repeated?
2/3.
What is 0.4 repeated?
2/5.
That would be 0.4 would be 2/5, but 0.4 repeated? 4/9. What do you suppose that 0.8 repeated is? 8/9. How about 0.1 repeated? The reason I brought these up first is because you're familiar with them, but isn't 1/3 the same as 3/9? And isn't 2/3 the same as 6/9? Okay, and these are some others you're not quite as familiar with. Here's the really interesting one that has a little to do with what we did today. What is 0.9 repeated? 1. People go, no, it's a little less than 1. No, it is 1. Because it's 9/9. If you let the 9s go forever, you will arrive at the number 1. But who can let 0.9 go repeated forever? You can't. So you have to try to imagine it. But if you do, you'll arrive at 1. Now, let's see if you can extrapolate, carry it a little bit further. Can anybody tell me or guess, an educated guess at what 0.34 is repeated? The whole 3/4? What is that, do you think? 34/99. Yep. Check it out in your calculator. You can check that out. Check out any of these. What do you suppose 0.873 repeated is?
873.
Yep, 873, 999. Which is kind of cool, right? So if they give you something that doesn't have a repeat bar over it, but goes like this, I know I keep lopping off more and more of the board. You have 0.127812781227, and they go like that. You got to find the repeater. It's right here. And you put that number over as many 9s. Okay? And it does have to do with geometric sequences and series, but I'm not going to show you why. Not here. I just wanted to show you this cool thing. It's over as many 9s. Now, what's interesting about this is if you have just this and it truncates, we call it truncating. Another lop off here. If I have 0.1278 stop, and it just stops, we call it truncating, it doesn't have any more repeaters, then that is 1278 over the number, the power of 10 that has that many zeros. Okay? You following? Had to be now, huh? Okay, so if it stops, you put that number over the number with as many zeros, but if it continues, you put that number over as many 9s. They're only different by a little teeny tiny smidgen, but it's this smidgen that makes it different. Okay? Everybody good? Okay. Those of you doing it on paper, here's the assignment. Give you a minute to get your stuff out. Make sure that you're always checking the R value that fits the bill, because if it doesn't, you just write no sum and move on. Find R first. Okay, it is 7 through 15 odd. No, wait for- let's get to it. 7 through 15 odd, 16 through 19, 21, 23, and 30. Okay. Yeah, I haven't got much time, but you should be able to get a good start on this. Maybe finish it. See you, bye.